Okay, so let's get started with the meeting. Hello, I am Nick, and here to talk about procedural generation. You can follow along with the slides on dsuprog.club, and that'll also be how attendance is taken. And you can also ask questions from there if you're not in the Discord. And so let's get started. So first of all, what is it? That's always the best question to ask first of all. And basically, it's just randomly generating things, but with not entirely random. And so that encompasses a lot of things, including coherent noise, which we'll talk about quite a bit, fractals, which you've probably heard of, and we'll talk slightly less about because they're more complicated and there's a lot of them, and cellular automata, which is also, we're going to talk about that and more. Stick around, stay tuned. But first, we got to talk about the movie Tron, the 1982 one, Disney movie, and more specifically, a guy named Ken. And Ken was working on this movie called Tron, and he was all like, computer-generated images look too computer-generated. They don't look realistic. I can tell that they're too perfect. They're all just flat colors. So he did some math, and then won an Oscar. And this is that math. It's called Perlin noise, because he was called Ken Perlin. That was his name. And so how Perlin noise is created is you take a whole big grid, and at each of the grid points you draw an arrow randomly based on a random direction. And so then to fill in the grid at any point that you want to fill it in at, so if you're rendering it, it would be any individual pixel, you take, this is a bit math heavy, but you take the dot product of the vector from the nearest corner to the point that you're drawing it to, and the arrow at that nearest corner. But basically what that means is you're just giving it a value based on how close to that angle that given corner is. And so if you can see in these little squares, you've got a green side and a purple side and a white line, and those are generally perpendicular to the direction of the arrow. And so you've got just a bunch of different greens and purples fairly evenly spread out, but at random intervals, and evenly distributed too. It's not, you can't really have one whole big patch of just green or just purple. And so then once you have that, you just kind of smooth it out using the general things people usually use to smooth. It's more complicated math, so I'm not going to mention it. You can look it up. And then you've got this goop. Is useful for a lot of stuff. This is basically just Perlin noise given different colors based off of the value. It's not only Perlin noise, it's slightly adjusted, but this is basically an example of something that you can do with Perlin noise. And then here's a more traditional image of what you think of when you think of Perlin noise. Just a bunch of smudges. So then another thing you can do with Perlin noise is you can make Perlin worms, which are basically just lines drawn around all squiggly randomly. And Minecraft used to use it for their cave generation before they got all fancy with fancy math. And if I go back here, basically what those do is instead of taking all this dot product stuff, you start at any given point on the grid and then give it a direction and have it start going in that direction, but being kind of influenced by the direction of all of these arrows as if it were windy. So if I were to start near the top left here, let's say one cell down in the middle, I were to be going right, then this arrow here might influence it a bit up, and then it'd pretty quickly go off the screen, so that's a pretty bad example. But yeah, it just makes worms, Perlin worms. And there's a whole bunch of different variations of things you can do with that style of randomness. But general Perlin noise and Perlin worms kind of encompass quite a bit of them, if that's how you categorize them. Then one extra type of noise, kind of the next one that I tend to think of when I think of the different types of noises, is Voronoi noise, also known as cell noise or Worley noise. It's got a lot of names. But basically, you just draw a whole bunch of points on a grid. In this example, in order to be evenly spread out, there's 1 point per grid cell, but that's not a requirement of Voronoi noise. And the color of each pixel is determined by its distance to the nearest point. And so the ones that are close are black, farther away are white, and it kind of gives this cellular look, which is why it's sometimes called cell noise. And this is pretty useful for some water effects use it, stylized water, because you can kind of see the white parts here kind of look like cartoony waves, kind of like looking on water. There's a blue part and a white part usually, and a lot of the times people just use the white part of this for the white part. And another way that Voronoi noise is sometimes implemented is giving a color to each individual point and having the color of each pixel being determined by the color of the point that it's closest to. And this is just a visual representation of how that kind of works. The circles are going out to show the distance to that point, and then as the circles touch, it's showing that that's where they're evenly, the points there are evenly distanced from each of those 2 points. And so that's how you get those straight lines in that there. And something else is all of these, like pretty much every noise function works in basically any amount of dimensions, which is how you can do the Minecraft stuff. You basically just have to add an extra dimension to your array when you're working with it, and it's all the same concepts. In here it would just be cubes with a point in each cube, and then each point in 3D space has a different distance to each point still, so you calculate that distance. So this didn't format very well, but it's a link to a GitHub repo called Fast Noise Lite. There are a bunch of different libraries for many different languages for working with noise, and I'd recommend using one if you're gonna implement noise into your project, because it can be kind of complicated and unnecessary work when many people have done that same work before. But Fast Noise Lite comes with a graphical user interface here that you can use to play around with some different noise stuff. And it can just kind of show you, like, basically just what they look like more so. But you can also combine it with fractals, which I won't get into because this is starting to get a bit more complicated, but this is just kind of fun to play around with to make different things. As you can see, this is Perlin noise right here. Whoops. And then we've got the Voronoi noise, or this one calls it cellular here, and then the frequency is the size of the noise, with lower frequencies being larger because that's because the points are less frequent essentially, they're farther apart, so the cells look larger. And then as you increase the frequency, it appears to get smaller. And then the seed, this just shows that it changes completely even if you're just one seed value off. So it's pretty darn random, I'd say. Some noises that I didn't talk about in the presentation. This is open simplex noise. It's made by the same guy who made Perlin noise. Well, simplex noise is made by the same guy who made Perlin noise. This is an open source version of it, because there's some weird patent on it that people don't like to have to work around, so they made their own version of simplex noise. It's pretty similar to Perlin noise, but there are some advantages to it based on like processing power and implementation and stuff like that. More so with higher dimensions. So if you're doing something that needs 4 dimensions of noise for some reason, this would be probably moving away from the types of examples that I'm showing in this presentation, but you might need like higher dimensional noise depending on different things. This is faster in higher dimensions than Perlin noise, I think, is the main draw to it. And then value noise, let's see if I can, there, yeah. Value noise is basically just you take a random value and then assign it to each pixel and then blur the pixels. It's not a very good noise, but it is easy, and so it exists as its own separate thing. Oh, and then this is just a better blurring, essentially, of value noise. Yeah, so let's get back to the presentation here. And now we're going to talk a very small amount about fractals. Now fractals are good for procedural generation for 2 main reasons. One being that they have infinite detail, essentially. And so that's kind of what you want with procedural generation sometimes, is not having big smooth parts just randomly. You want to be able to have many layers of detail to simulate reality. And it's got repeated patterns that aren't always exactly the same. So for example, here's a tree that's a fractal, and it splits off to 2 branches at set intervals. Each branch splits off to its own 2 branches that each get smaller. And then if you added some variation to this, it'd be a fairly realistic tree. And you can get it to any detail level that you want to. And it's all just math. You didn't have to manually draw any sort of tree things. And then I kind of had to include this, the Mandelbrot set. It's the most famous fractal, I'd say. One of the more popular ones. Pretty cool looking. Not sure how it might be used in procedural generation, but if you're talking about fractals, you gotta include the Mandelbrot set. And then we have cellular automata. The most famous example of cellular automata is Conway's Game of Life, which you may have heard of. It's just a set of rules for a given set of pixels that are either black or white, and they live or die, in quotes, based on how many pixels there are around them. And there's a lot of cool things that you can make out of that. This is a pretty famous example. It's a glider maker thing. And this this part makes these parts, which just go off on forever. But one way to use this in generating infinite content is with caves of this type of thing. And so with this, you just, similarly to Game of Life, you have on and off pixels, off being empty space, on being walls. And then you can just start with randomly filling in, completely randomly, not with any like noise function or anything, filling in whether or not any given pixel is on or off. And then you go back through, and based on how many neighbors any given pixel has that are on, it'll be either on or off. So if there was just some random empty pixel in this top left corner here, that would get filled in with a wall because it's surrounded by walls. And so that makes these kind of organic looking shapes where the shape is random, but it's not like, but there is a shape there because it kind of condenses into these clumps. Condensing into clumps, I've found, is generally what people want out of procedural generation in a lot of cases. So something you may not realize is text is another thing that you can procedurally generate, and it's pretty useful to generate that. One of the most simple ways to do so is with Mad Libs. Similarly to the activity books, Mad Libs is you have a sentence and then you can have it fill in random words. The noun, past tense verbs, the noun. So the cat ate the cheese, the mouse drove the wall. And it doesn't always work out, but if you curate a massive list of the categories of words you need, you can use this to pretty good effect in certain applications. I believe this is how things like D&D character ideas generator and stuff like that works usually. That tends to seem pretty random, which is good for procedural generation, but also sometimes not as good. It's a fine line between seeming random and seeming not random. A bit more complicated, and a bit less curated also, is the Markov chain. And basically, Markov chains just take in massive streams of text and determine what the frequency of any given combination of words is. So you start with some word, well, let's say it starts with Frank, and then it goes through all the other words that have ever come after Frank in its data set. And based on how often that word appeared after Frank, it'll randomly select one of those, weighted towards the ones that have appeared more. So if Frank is someone who eats a lot, then you might say it might come up with Frank ate more often than it comes up with Frank Sinatra. And this usually is, I find that this is most often used in a more of a novelty context than a serious one. Like, a lot of the times it's just, can you tell this AI generated a text message from real ones from certain database? But there are uses for it. Now, for the last slide, I just have it labeled other things because as I was making the presentation, I realized that there is a lot of miscellaneous info that I wanted to share that didn't really fit into a good number of slides. So here is some coherent rambling about coherent noise. So one thing is, when you're doing procedural generation, a lot of it is more than just or needs to be more detailed than just this type of cloudy mess. And so when you're actually working with procedural generation in a sense where you need a specific outcome, a lot of the time you can look towards science in that field in the real world to determine ways that you can make things look more realistic. So for example, this is a Whittaker diagram, and it shows it shows what biomes are which based on the average temperature and annual precipitation. And so I believe that Minecraft uses this to determine its biomes. And essentially, instead of having to randomly clump up sections and be like, okay, I'm going to determine that this is a tundra or taiga based off of just a random value, you can have like a Perlin noise cast over the whole thing for average temperature, and then another one for annual precipitation. And then at any given point, you can just look up that noise value and be like, hey, this is such and such temperature and such precipitation. This is a temperate rainforest, so the grass should be this color. There should be this % chance of a tree being here. And so that way you won't have a tundra being right next to a tropical rainforest, for example. Other examples of this type of thing include like erosion models and stuff like that. Also, going back to this image again, multiplication is used a whole bunch, and so if you want a more detailed thing, you can take a big one of these and a small one of these. I'm going to switch over to the noise generator so that there's a bigger example, and I closed it, so 1 second. There we go. Okay. So for example, you could take, need to get rid of the fractals. So you could take a Perlin noise with a low frequency or a high frequency like this for the finer details, and then multiply it with something more like this, and then that would essentially just give all these blobs jaggy edges, which you might want depending on what you're doing. So you can also do a bunch of different stuff with, if you have a bunch of different types of noises, which is why it's good to know about all the different types of noises, because they all have their different applications, but sometimes there's carryover. Yeah, just math. When in doubt, do more math. That's how procedural generation works. Find some math to do it, and it works. That's how Ken Perlin won an Oscar. I believe that was all of the other things I had, but does anybody have any questions about procedural generation that they could put in the YouTube chat or Discord or questions page on the website? I'm going to consider that to be a no. So for these last couple of minutes, I'm just going to show a couple of examples of good resources for procedural generation. The Book of Shaders is a good website for shaders, but they have a generative designs category here that's been incomplete for a while, so I think they're kind of done working on it potentially. But it has some good stuff about generating different types of noise, and also there are some examples about cool things that different people have done with them. This is pretty cool. It's taking the equation of circles going outwards and using that to determine how far away from the Voronoi noise points it should draw outwards. And so, yeah, you can kind of get inspiration for what types of math to do with this type of thing. And that is something that I probably should have mentioned in other things, is that you can just use basic math equations to do some cool things, like this circles going outwards. Doesn't have to be like noise functions. Scrolling lines is another one that usually works pretty well for certain things. And then let's see. It also has some stuff on regular noise here. There's that same image I used. But yeah, it just goes through it pretty well, I would say, and also shows some good examples. Here's a wood texture made from noise. Then the other one, oh yeah, libnoise. I'd say one of the more popular noise generation libraries. The other one I mentioned was fast noise, which is basically small and fast, and this one's just kind of general purpose. But there's also a bunch of tutorials that have different projects. This one is where I took that image from earlier for the example. And it just goes through and shows how you can do more math. That's basically the moral of the story, is do more math. Math makes things cooler. When in doubt, math. And so, thus ends this presentation. I hope you enjoyed it. Thank you for